I'm a former electrical engineering student at U of R, so an alumni. And I've also worked a year in industry before going to grad school, so I can kind of give a little bit of an overview about some differences between industry and graduate school and what you can expect kind of going into both, or at least from my experience. So I'll start sharing my screen here. Can everyone see this?
Yes.
Perfect. 1 second. Okay, great. So I'm just, like I said, I was going to start with how I kind of got started in robotics, then some like my experiences doing research at Rochester and other kind of stuff I've done with robotics at the University of Rochester. Then some industry experience I had, and then my current work at CU Boulder, which is with the DARPA Subterranean Challenge. So first, kind of how I got started in robotics. In high school, well, actually my 8th grade year, so in middle school, I joined the high school first robotics team. And so that was kind of my first experience with robotics. And I really, mostly there, I did programming and like electrical wiring for the robot. And I really liked that kind of hands-on experience. And wasn't sure really what I wanted to do in college, but knew I wanted to go into engineering. So I kind of chose electrical engineering and liked the program. And then I met Dr. Howard at Rochester, took his classes, and then ended up doing research with him. So that was how I kind of continued into that. So what my research dealt with at Rochester was motion planning with state lattices. So for those who aren't familiar, the general kind of problem in motion planning is how do you efficiently compute a path from point A to point B that accounts for the robot dynamics, so how it's going to traverse over the environment without colliding into things and not getting stuck. And the challenges there is that space is basically infinite. So you have to do some kind of discretization to search through it in order to find a feasible solution. It's basically a polynomial type problem. So one way that's done in robotics is using a state lattice, which is a really memory efficient way of encoding robot dynamics into this kind of recombinant lattice, which is very easy to run a graph search algorithm on. I'll have a little bit more examples in the next slide. So in that lattice, you build a graph up. So each node is like a sample of the state space, usually sampled based on a discretization that you choose ahead of time. And then each edge between the node represents a feasible action the robot could take to get between nodes. So at each kind of node, you have what's known as a control set, which is the sample trajectories, which are generated using polynomial spirals. So for instance, this figure right here on the left would be if the robot's pointing in this direction. Can you guys see my mouse moving?
For me, it's still on the, okay, just change slides.
Oh, okay.
I can see the mouse fine.
Okay. So if the robot's pointing in this direction, these are all, for instance, these are some sets of feasible actions it could take. The turns encode the dynamics. So those are actual actions that the robot could turn. It's not something that's like a jagged path that you then have to write a much smoother path following controller to follow. With these methods, you still need a path following controller, but you can kind of follow these projected spirals a lot easier than like a jagged path. So kind of what we did with this approach is a traditional state lattice still kind of generates paths that will sometimes not necessarily take the most efficient route due to the sampling discretization you choose ahead of time. So one thing that Dr. Howard did for his thesis at CMU was use a gradient descent type process on each node to perturb these paths and kind of sneak around the areas that you otherwise wouldn't know based on your discretization. So you're kind of following the gradient of the environment to get to there. And so one thing that was kind of noted in that work is it's pretty computationally expensive to run gradient descent on every single node in the environment. So we used a neural network to predict where you would want to run it based on the terrain of the environment to try and reduce that overall complexity. And that did reduce some of the computation time pretty significantly by kind of a factor of 2 or 3. And so that was pretty encouraging. I do know that this has since improved a lot based on some future conversations I had with Dr. Howard. So if anyone's curious, I'm sure he'd be more than willing to talk more about this, but I can also answer, I can go more in depth into the method, answer any questions. I think someone's on mute.
Yeah. So actually, I had a question, and this just be so for context. I'm like a mechie guy, so I'm just going from this from a little more outside perspective. But I was curious. In that first method, the SL, I saw that the time is like really really small compared to like all the other stuff. Is there like a reason for that? Why that's so quick?
Yeah, absolutely. So the gradient descent algorithm is essentially doing an iteration-based approach following kind of the gradient. So each node you have to do that process, and that process is kind of the slow bottleneck piece. So the stateless approach doesn't do that, but as a result, it also can't get around certain areas and has to take kind of the long way around because it doesn't know they exist. Because you chose like a coarse discretization at the beginning. But on the flip side, if you sample finer, then your search algorithm takes a lot longer. So that's when these algorithms tend to do a lot better, like the adaptive version and then the predictively adaptive version do a lot better on longer environments because they cut down both the path cost and because the discretization is finer, the search does not take as long, or discretization is more coarse, rather.
Okay, that makes sense. Thank you. Yeah, thank you for the clarification.
Yeah, no problem. So then after kind of I graduated from University of Rochester, I was kind of torn between grad school and industry, which I'm sure some of you probably will be. I don't know, what years are you all in?
Yeah, this is small enough. Maybe I'll introduce ourselves. So I'm currently a junior majoring in CS and linguistics. I'm actually researching with Professor Howard now as part of Rail, and
Great.
it's kind of a random plug, but like our research is, we basically made a discrete version of the adaptive stateless and a bunch of stuff. So like this is, I've definitely read the PASL paper and cited it now. So it's great to see that.
Excellent.
Yeah, I'm a junior majoring in computer science right now, minoring in electrical and computer engineering, actually. Yeah.
Great.
And I'm a mechie sophomore, going to be junior soon, with a minor in chemical engineering and material science, and I also do research in with a professor on campus, or professor at the U of R. So yeah.
Great. And just for context, like while I was at U of R, I also did the Baja Club and I did Engineers Without Borders. So I don't know if any of you are familiar with any of those clubs or have been a part of any of that, but that's kind of more of my background. So like I was saying, I had a tough time deciding between industry and grad school. So I ended up deciding to try industry for a year before going to grad school. And I took a position with a company called Protodyne based in Windsor, Connecticut. And what they do is they automate a lot of the kind of lab work. So in blood drawing process, or rather analyzing the blood. So every time you go do blood work, you get a test tube drawn. And then it needs to get sent off to a lab somewhere to kind of analyze that and give you your test results. So they have these kind of massive automation systems that take all those filled tubes and process them and then do like the pipetting action to put them in exact amounts into different analyzing machines and then kind of automate that whole process. So I did that for about a year. And during my time there, I primarily worked in Java for the software language, some JavaScript, and I mostly handled like kind of big data analysis type stuff with different medical records and how to handle all like the sheer amount of data that was coming through and make it efficient for both querying later and different kind of analysis tools. And overall, I'd say like it was a great experience, but what I found was that in industry, at least I was more interested in solving kind of problems that hadn't really been attacked before. And a lot of the problems I was solving in industry were problems that there was a solution for, and you really were just kind of like re-implementing something that already exists for the company or doing an incremental improvement on something that already kind of existed. So I actually grew kind of bored after a little bit. So that's kind of what pushed me to go more towards grad school. So right now, like I said earlier, I'm at the University of Colorado Boulder working in the Autonomous Robotics and Perception Group, which is advised by Christopher Heckman. And so one of the projects he had when I came on board, which I was super excited about, was the DARPA Subterranean Challenge. So that's a huge competition that's being put on by DARPA right now with the goal to basically figure out how to explore underground environments efficiently for like search and rescue type operations. Now, there's tons and tons of challenges associated with that. So what they want us to do is send a robot underground, have it explore the environment, and autonomously report back where different kind of artifacts are located. So they provide the artifacts kind of ahead of time and give you this localization point. So your robot's traversing through, and we use like convolutional neural networks to detect these. So once you detect them, you have to then send it over to DARPA to an accuracy of 5 meters from where the actual ground truth location. And to get a ground truth location, DARPA goes through these environments and uses like professional grade survey equipment ahead of time to know exactly where everything is. Now, can any of you think of like challenges for sending a robot underground and like what some of the major challenges are to accomplish this type of task? I know this might be putting some people on the spot, but I'm trying to also make this a little bit more interactive.
I would say there's like generally poor like signal connectivity underground. So like Wi-Fi is like pretty bad. So you'd be relying on more like local signals.
Yeah, absolutely. One of the things is we have the opportunity to send data back to all the data to get to DARPA has to be sent back to the entrance. So I'll talk a little bit about more of this later, but we do a mesh networking solution to help with that. But Wi-Fi is a huge challenge.
You might also, I don't know if this is part of it or this is anything that would run into, I guess, but in terms of like, if you wanted any like visual feedback, it might be, I mean, it's probably going to be very dark in there. And so if you wanted, like, if you need any like mounted cameras, you need some form of light or some other ways to see in like pitch black, basically.
Absolutely. That's another big challenge is finding the right kind of balance of lighting on the robots. We're using basically we're using 8 10-watt LEDs right now to light up our camera system.
I don't know if this is one of the things you're looking for maybe, but like because we're underground, we don't really have a map, obviously, and we also can't communicate via GPS or anything to get a map. And so like, where is the robot? How does it know where things are in relation to itself? This seems like a big problem.
Absolutely. That's one of the hardest challenges here. And the last thing is, how do you plan for these environments is another significant issue once you get the map. Exploration is on an unknown environment is kind of a entirely different animal than exploring a known map. So kind of to get into that, DARPA divided this into 3 different events: a tunnel circuit, an urban circuit, and then a cave circuit. And then there's a final event, which will combine all 3 circuits. So we competed in both the tunnel and the urban circuit. And unfortunately, the cave circuit, due to COVID restrictions, was canceled. And there's only the final event. So the tunnel circuit primarily dealt with mines. And it was held at this NIOSH Safety Research Mine located in Pittsburgh, Pennsylvania. And at these events, there's about, I think at that event, there was 10 systems track teams. So there were, for example, there's CMU has a team, JPL, MIT, and Caltech have a collaboration on a team. There's CU Boulder, there's ETH Zurich, and I forget who they partnered with. One, I think Berkeley maybe. There's like a whole slew of both international and national teams competing for this. There's 2 kind of tracks. There's funded teams, which means you got a grant award from DARPA, which is what we are, or you can compete without any kind of award, and then you can win prize money at the end of it. And these prizes are actually pretty big. They're on the order, I think first prize is like $1 million. But keep in mind, building up this type of system, probably, if you get that $1 million check, you're probably just paying yourself back for all the effort you put into designing and building the system. Or you might not even be breaking even. So it sounds big on paper, but robots are expensive. So at the tunnel circuit, as you can kind of see here, we used the ClearPath Husky primarily. we did modify significantly from what they ship stock. So on the back here, you can see that's one of our, that's a TP-Link router that we initially used for our mesh communications. Then inside here, we're actually running Ryzen Threadrippers with an NVIDIA 1650 GPU for kind of our object detection. And there's actually on each one, it's a little hard to tell from this picture, but like right here, they were actually liquid cooled at that time. So we had robots with like active liquid cooling for the processor, which was definitely an adventure setting all that up. Now, I know people brought up mapping. So we ended up trying out both visual inertial based SLAM solutions. So those are basically taking a camera and doing feature tracking between different frames combined with the IMU to determine where you are, which we found were not very reliable in these types of environments due to the lighting conditions. And when you illuminate these environments, you get something known as specular highlights, which breaks a lot of the traditional kind of key point matching algorithms. So what we ended up moving towards is a LiDAR inertial based SLAM solution, which we use the Ouster 64 beam LiDARs located on top here. And those do scan to scan matching combined with IMU measurements. Specifically at this time, we used a modified version of Google's cartographer package. One thing to kind of note was when you do a challenge like this, you'll find that at times you wish you could kind of like get into and write everything. But if you want to have a product that works and succeeds all the time, you do have to use a lot of open source software and modify it to your needs. Just between these events, there's only 6 months. So there's like a really high rate of development time, or high rate of development that needs to happen in a short amount of time. So I kind of wanted to show, this is a kind of from the robot point of view, what the environments look like. So part of the environment, DARPA does a good job of lighting up for you. We also have the lights on the robot. Other parts are dark, but this is one of the mines at the NIOS Research Center. And our robot right now for getting around is actually building a graph of the environment and just selecting points down the graph. And path following is actually, we did a really simple solution for the tunnel environment, which is just to try and center along the walls and keep the robot in the center. We made that kind of strategic move just because it was something really robust and reliable. And with these environments are relatively non-complex compared to what we'll see later at like the urban environment. But one of the aspects that we're going to see here in a minute is DARPA doesn't like to make things easy. So they also deploy fog into these environments, before we get to that, that was one of the examples of an artifact that you have to report back. So we would be sending that back to the base station at that moment. But I forget exactly what it is. The fog is coming up. And the challenge with fog is your LiDAR sensor doesn't really see through fog that well. Neither do cameras. So we are looking at using radar to do some state estimation in conjunction with the IMU, similar to like LiDAR inertial SLAM, but with radar. That's still highly in kind of the research phase, and I'm not personally working on it, but that's something our team is working on. And then the other kind of thing that took us by surprise with this environment. So like one of the artifacts was a red backpack, and they had all these red markings on the wall. And so like we train weights, and then all of a sudden we'd get these reports back for these red markings that would be unexpected. Because like the mine we tested in here was a gold mine and it wasn't. And for context, those markings are, they're kind of, I think FEMA or somebody puts them in when they go and do safety in these mines. So we didn't really expect that, and definitely threw us a little bit off course. And at that point, we were trying to send images back to the base station, but due to that Wi-Fi constraint, they weren't always coming through, which was definitely a challenge to tell. Obviously, at our base station, there's one person that can look at all this data. Everyone else can't, so you have one person kind of operating all the robots. So they can make the adjustment and send it to DARPA if they saw like it was a backpack or it was a fake object. They could decide not to report it. But without an image, it's really hard to decide anything. So this is where the fog came in. And you'll kind of notice our robot's moving really slow. Fortunately, this isn't very dense fog, so it can kind of tell where things are, but not very well, which is why it's kind of being so cautious. And yeah, so that's kind of what the tunnel environments look like. So these are kind of overall maps of the environment. And these are actually the areas that we ended up exploring are highlighted in blue. So at this event, we ended up coming in, I believe, 4th out of 10, just exploring these areas. So only one team really was able to explore most of the environment, and that was CMU. And they were, at this point, the clear leaders in the pack, as kind of expected for those of you who are familiar with the past DARPA challenges. CMU tends to do very well and has a lot of experience in them. So this was one of the courses, and then they had a second course, and you got 2 runs on each course. This course, I'm not sure why they don't have our map pilot on there. DARPA sent these to us afterwards. We definitely explored more than that, but so as you can kind of see, this is why we chose to use a graph planner, because you can generate a node at each intersection and really easily tell where to go. There's not much variation on what you can do here. These are very narrow corridors, not wide open space. So that approach ended up working really well for us at Tunnel. Like I said, we got in the top 4 for scored artifacts, which was better than we'd hoped to do based on where we were at that time. Any questions about kind of the tunnel circuit?
Yeah, so I have a question real quick, and this might be a bit of a basic one. I missed the first, I guess, like 10 minutes, but like, what's the like limit on the like autonomization of this robot? So like, I'm a little bit confused. Like, you know, so you're saying like there's a person actually like piloting this robot as it moves through these tunnels, right? But is it supposed
Not
to?
quite. Not quite.
Okay, so it's actually autonomously trying to map this thing itself.
So yes, so the primary goal is to have everything autonomous. And then we have a pit crew who can do like the initial setup to launch robots. And then there's one person known as the human supervisor who can actually get the map data back, get the artifact reports back, and see what the robots are doing. And they can go ahead. Some teams at Tunnel did actually go, and that human supervisor could teleop them. But due to the comms range and stuff like that, that's not really an effective strategy. DARPA really wants you to do autonomous. What traditionally we do and most teams do is you can sometimes, if the robot gets stuck or something, you could send it a waypoint and then it will continue planning to that waypoint autonomously and continue on its exploration. So you can kind of interject briefly if something abnormal happens, but for the most part, the goal is to have these be entirely autonomous.
Okay, yeah, that makes more sense to me. And it's also supposed to be autonomous in terms of like this artifact detection, as you're mentioning. So, you know,
Correct.
like maybe it sees the red backpack and it has a list of items it's supposed to detect. It's like just crosses red backpack off the list. So if it sees anything else that's red and like squared, doesn't bother dealing with that anymore.
Not quite. So there's, at this event, there was 10 artifacts spread out and there was 5 total available, but then tell you which 10 they were going to be. So you didn't know there was necessarily going to be 2 backpacks. It could have been like 3 backpacks. So really the approach we used was a variation. If any of you are familiar with the You Only Look Once paper, YOLO, we used the variation of that to kind of train a network and predict objects. And then we had real sense cameras. So we take the depth stream at where we got the projection in order to get a 3D point in the environment to localize on. And as I kind of showed earlier in one of the slides, DARPA has these kind of localization points for each object. But to the best of my knowledge, no one really is targeting the localization point because they also specify it has to be reported accurately within 5 meters. So if you report any point on the object, it's as long as your state estimator is close enough, you're going to be within that 5 meters. And one thing to note here that I was going to get into a little bit later, but we can talk about now, is the cell phone also broadcasts Bluetooth and Wi-Fi. It's a very hard object to detect visually because it can be in any orientation. So you can imagine if it's flat on a table, any kind of visual detection method is not really going to tell what it is. And then I had CO2 gas, which we use a kind of gas sensor to detect. And that one's pretty simple. The sensor basically reads the level of CO2 in the environment, and DARPA specifies if it's above this level, there's that artifact. The challenge there is they want you to detect the door next to that artifact. We currently don't do that. We may end up doing that, but we just report where the robot was when it detected it. And that scored us at the urban event. They had that artifact that scored us every time for the artifact. So we didn't really see a need to develop that kind of doorway localizer. So any more questions about tunnel environment or like anything else about this?
I was curious, like, I saw in the video, like, it like turned left and then like it got kind of stuck. How did it eventually like correct itself to get back to the main pathway? Because it like it went back and saw the same artifact again too. And then it finally realized it should go forward. Like how did
So
it do that?
one of the things that happen that our strategy relies on is if you don't have comms, it will go plan its way back to the entrance until it gets comms to report an artifact. So that's probably why it was going back at that point. Without seeing the actual data, I don't know necessarily for sure. But we also have, if we get into a corner, we had different kind of routines to get it unstuck that we would run. It was really a state machine at that point. So that was a reactive based type controller. So it would kind of just try to wiggle its way out and eventually find its way out. And that worked for us most of the time.
Okay, yeah, that explains it.
So the next kind of event that DARPA had us do was this urban circuit. So one of my questions kind of for you all just to pose here is, what kind of challenges would you expect to be in like an urban underground environment as opposed to a tunnel environment that would have to overcome?
Well, I think as you mentioned, it's definitely a lot more of a complex environment. So I'd expect a lot more like twists, turns, things that might not necessarily be like methodically planned out, so to speak. So like with a mine, you know, like it's, you know, you don't have like an average member of the public walking around in a mine, so they're not gonna like affect its environment much. But in an urban environment, you'd probably have something, you know, maybe someone like randomly leaves out a traffic cone they forgot to pick up, stuff like that. That might be marked as an artifact, even when you don't intend it to be.
Yeah, for sure. That was one challenge. Anyone else have any ideas? So I can kind of get into this a little bit more then. So one of the big things that we had to deal with is stairs, which, as you can tell, like the Huskies do not go up and down stairs. These are DARPA explicitly said these were going to be multi-storied environments. Then railroad tracks are also kind of a big obstacle to get a robot over. And these next two all kind of relate to localization. So LiDAR-based localization typically does scan-to-scan matching, but when you have like urban environments that are built up and human-made, sometimes, especially if they built like a hallway or something, it's going to be very repetitive. So we were concerned that the LiDAR scan-to-scan matching, the scan matching would tell us that the robot's standing still, but the IMU is telling you it's going forward, and then the robot doesn't really know where it is because it has two pieces of conflicting information. Fortunately, that wasn't as big of an issue. And then the other kind of challenge is 3D localization in tunnel. We decided to only localize in 2D because we knew that the environment was mostly planar. But here with two stories, you can no longer make that assumption safely and score things accurately or plan accurately over the environment. So this event took place at this abandoned nuclear kind of power plant in Washington State. They, I guess, were building this in the 70s when like nuclear power was a huge thing, and then lost funding. I think it was shortly after Chernobyl. They also just decided to discontinue it at that point. And now there's just a giant kind of abandoned structure there that apparently people rent out for like movie sets and stuff, and the ARPA decided to rent it out for this competition. So going on to like those challenges, one of the things we tried to do differently for urban, sometimes successfully, sometimes not as well, is we bought these HD2 mobile tank platforms and built those up, which can go up and down stairs. It's pretty clunky, but they can do it. And then we also put a significant time and effort into developing a UAV-based solution. as well as continued using our Huskies. So just for context, I don't personally work on the UAVs, but some of the challenges there are the compute is much less powerful than the Husky. It's just an Intel NUC kind of i7 processor, and they only have 10 minutes of flight time. So they really need to have much more efficient planners on them because 10 minutes doesn't get you very far into the environment. What we are currently working on now to solve that issue is to mount a UAV to the back of the Husky and launch it inside the environment, but that was not something we had the capability of at the urban event. So this video is sped up to 4x kind of the speed, but this is an example of our frontier-based path planner, as well as our mapping technique as we go through the environment. And one of the things you'll notice is at this point, you can kind of see the lights moving around. We had a camera on a gimbal to try and look at more areas of the environment. Another kind of challenge is the tunnel circuit, the ceilings are low, so you don't really need to look up anywhere to look for artifacts. You can kind of get away with doing like 4 cameras mounted all the way around the robot. But here we kind of assumed that we would have to be the gimbal camera, which ended up not working as well as we'd hoped due to motion blur and things of that nature. But this is kind of an example of how the robot progresses through. And what you can kind of tell here is there's 2 maps. The smaller map is what we're planning over, which has to do with how far we can see the artifacts, which is about 5 to 7 meters. So we don't want to plan in areas where we can't see the artifacts yet. And the larger map is coming from the state estimator. And the smaller map is the 3D map generated. It's a adaptation of Octomap that we use that also supports like map differences and merging maps between robots and things of that nature.
Could I ask what the different colors are in the cost map? Like, is it just cost?
Absolutely, it's height of the obstacle, purely height on that map. Other questions about this kind of video?
Do you wish you guys didn't use that camera that caused motion blur?
So this is kind of more of an aside. All of our cameras were Intel RealSense at this time. And the RealSense, while it's an inexpensive sensor that does RGB and D, they are not the most reliable thing out there. We had a lot of issues, and it was both motion blur and these cameras were frequently disconnecting. They not the cables disconnecting, like it would just disappear off the USB bus. And at one of our runs, it not only took itself off the USB bus, but it also took down the IMU. So that kind of rendered the robot useless. And we traced all of this back to the Intel RealSense driver. It turns out that they actually pushed a commit for the Intel NUC BIOS to, I think it was something like fix reliability issues with RealSense camera. Or that was like what the BIOS changelog said. So we're using AMD Ryzen Threadrippers. So naturally we weren't getting much support from Intel on that run. So we heavily decided to pivot after this event away from those cameras. And now we're using Gigabyte Ethernet cameras, and we actually align our cameras to the LiDAR and use the LiDAR for depth measurements to localize the artifacts. So we visually detect them in the camera stream and then use the LiDAR to project to 3D, which has been so far more reliable in our testing than the Intel RealSense cameras ever were. So from my experience, if any of you are planning to use Intel RealSense cameras, if you want to use one, it tends to work really well. Sometimes you can get away with 2. If you're trying to go like 4 or 5 like we were using, it's not the best idea out there, at least on a single computer. Now, this was almost a year ago, so maybe some of this has been fixed, but we just had the sour taste in our mouth and didn't want to see if it had been fixed.
I have a question real quick about the UAV you were mentioning,
Sure.
and how you said it really only worked for about like 10 minutes. And then so you're saying that one of y'all's plans was to have it mounted on the back of the Husky, like the roller fellow?
Yeah. So you see how this has a bunch of open area right now on the Husky?
Mhm.
We're designing a gripper-based solution to actually hold down to the legs of the UAV. And then as we go through the environment, we can release the gripper and the UAV can actually take off from the Husky. Or that's in theory what the plan is. That stuff is still in development.
Have you got? Oh, what were you
ahead.
gonna say?
I was gonna say, to be honest, the UAV didn't work so well for us at the urban event. We just kind of finished getting it working and tested like 2 weeks before, and it wasn't tested that well. So it flew for a little bit and then kind of immediately needed to land due to constraints in the environment. But it's come a long way since then. So we're hoping it's going to work a lot better for us in the final event.
Have you guys had any improvements in its like flying lifetime? Like you said, it's about 10 minutes, right?
Not really. The big trade-off there, from my understanding, is LiPo batteries can only carry so much energy density per weight. And with the UAV, it's very diminishing returns. You can put a bigger battery on, but then you're carrying that weight with the motors. So you're draining more power anyways. So at a certain point, your kind of weight to power curve doesn't handle so well. So just adding more batteries, you actually lose flight time at some point because you're carrying that extra weight.
Have you guys put any kind of thought into having like, the reason I pitched this is because we actually have a team here at like UR Robotics called the Solar Team that's currently working on a mobile like recharging station, basically, because at first they also want to have an autonomous flying drone. So like, what do you guys have any kind of plans in the works as to how to extend the lifetime of this UAV without, like, you know, as you're mentioning, the weight power curve is not really going to take you anywhere?
Honestly, our solution is to mount like 3 UAVs, one to each of our 3 Huskies, and just have them explore different areas right now. We're not really looking at trying to recharge them mobily, because these batteries right now do take probably a good 30 to 40 minutes on one of our LiPo chargers to charge up. So just like these are, I don't know if I mentioned it, but these are hour-long runs total. So it's not really practical to try and recharge these batteries in the field. And the other kind of challenge with that is, right now the UAV kind of takes off and then it can find itself a safe place to land when it's running low on battery. But getting it to re-land on a robot or onto a charging station is a much harder problem than just having it find like a flat piece of ground to land and not crash. So there's kind of a lot of areas you could take it. One team to solve the flight problem actually is using blimps to flying time problem and trying to move their blimps around. That has been met kind of mixed success because there's a lot of ventilation kind of shafts in these places with fans, and blimps don't tend to do well with like air blowing and pushing them in other directions. But they do stay up for most of the competition. They just didn't seem to necessarily go where the team wanted them to go all the time.
I see.
Could I ask what, does the competition require the use of UAV, or is it suggested?
It does not explicitly require it, but especially in like the cave circuit, we didn't have it, but they said there's gonna be steep drop-offs and things where a ground robot couldn't conceivably even cross. So in essence, no, but you would have to come up with some other solution other than ground robots if you want to explore everything. But you could potentially not have a UAV and still do relatively well, because even the top scoring teams, I think the highest score was like 10 or 11 of the artifacts. So you can imagine if you explore the areas you do well and you can find all the artifacts in the areas you do explore, that might be enough depending on what the other teams end up doing.
Apart from just going, you know, those places the mobile robot can't, or the ground vehicle can't, like, do UAVs have other like sensing benefits, or is it just that reaching other places mainly?
There's vertical shafts that they can go up in the environments that DARPA has explicitly called out multiple times. And one strategy that we're considering using is the UAV can map higher up and get kind of a better overview of what the environment looks like. So if we send those maps back to, either we'll write something to autonomously look at them and interpret the environment, that would be the goal, but more than likely we'll send it back to the base station and our human supervisor can send kind of a waypoint to go into those areas based on what the map from the UAV provides. So they do have the advantage of that high vantage point. So I know someone had asked about like the Wi-Fi underneath. So that's one of our biggest challenges, and most of us are kind of want to work with robotics and less with Wi-Fi networks. So that's kind of been a huge challenge to develop along the way. I ended up doing a lot of this. So our beacons have greatly evolved. At the tunnel circuit, we deployed these really small beacons that were pretty low powered, and we want to string together a bunch of them. And that was based on a misunderstanding of the rules. DARPA told us that we may or may not get these beacons back after each run. And the radios that went into these two beacons cost about $1,000 a piece, and they have 2 watts of transmit power. So naturally, dumping $1,000 into each beacon and not getting it back at the end of like the competition would have been really bad for us. And then we got there and it turned out they were giving it back to everyone. So that was a little unfortunate, but definitely changed our strategy. This next beacon was kind of developed by a team of undergrads who really wanted to use, that's actually a Mazda Miata antenna. It's the smallest kind of car antenna you can buy, but we wanted to get extra height on the antennas for the urban environment because the higher your antenna is, the better coverage you get overall. So that's one of the things we learned. However, we also didn't have enough beacons at that point. So that's why we moved to this really kind of aluminum-based case design, which we're going to be using now for the cave circuit. And we're actually working on a more miniature version. And the trade-off there is lower antennas, but we can also, they're higher powered radios than the tunnel ones. So they seem to be working pretty well closer to the ground. And what these radios do is they each connect to each other. And it's basically like a giant mesh network. So they hop between radios. And as long as you have a connection back to the base station, you can transmit data that way. And the other thing our team does is each radio also has a Odroid on it with like an SD card. So we can store data on there. So if we do have a disconnect in our comms network and a robot passes by that beacon, it will offload the data and it can ferry it back to like a different section of the comms network to send it back to the base station. Because this is also an autonomous type operation of knowing where to deploy these beacons, and it's based, right now it's based mostly on distance. We could look at RSSI values, but those, for anyone who's been in the wireless space, are not the most reliable indicator of how close in coverage. And we also do turn around if we lose comms coverage to try and deploy another beacon, but it still only kind of gets you like 80–85% coverage at best right now. So that's one of the reasons this is a huge challenge underground. And the bandwidth is also quite limited for these. You're looking at like 5 to 10 megabits per second. And as you do more hops, the bandwidth also decreases. So that's why we've compressed almost everything that goes over this network now, which is something we definitely learned over the competition, like how much we can and can't send back. For example, at the urban competition, we were sending way too much map data back, and we actually transmitted like 2.5 gigabytes in the course of the hour run, but we didn't get the information we wanted because it was all this like map data that was trying to come through and just too much.
I see. And if you don't mind me asking, you said that these beacons cost like 1 to 2K a piece.
Yeah, the primary radio in there is a Doodle Lab. You can look up that company, but they're like a smart radio. And they're really based on a $30 like AF9K series processor, but their front end is in that form factor. You don't have many companies putting out like 2-watt radios on the Wi-Fi bands. So that's what you're really paying for, is their kind of RF front end to the whole radio.
I see. So are you saying it was more of like a, sorry, I guess since I was the one who asked the question, I'm like particularly interested in this like principle of trying to use this like mesh network of beacons. I was actually talking about it with Bennett the other day. So like, is this some kind of form of like software defined radio where they're just having this like entirely reconfigurable like system at each call?
If you look at what something called Batman ADV, it's a mesh routing protocol that runs on layer 2. And that's what we initially used. Now we're partnered with a company called Meshmerize, who one of their founder wrote most of Batman ADV and then has made significant improvements to that. And now it's a commercial product. for kind of the mesh routing algorithm. One of the issues we had early on with Batman was the reconnect times were between 5 to 6 seconds, which was a little long for us, especially in these kind of dynamic environments. So like Mesh Memorize brings that down to sub-second reconnect times if you go out of range and get back into range. It's a little less of an efficient, it's more of a greedy algorithm for like the mesh protocol from my understanding, based on what we've gotten from the company. So it's a little less efficient sometimes to pass, but you're guaranteed to have a route most of the time that there's one available, as opposed to spending time searching for the optimal route. It will just greedily choose a route that's available and then correct for an optimal route if it finds one later, which kind of guarantees you're getting data if you get any kind of connectivity, as opposed to waiting for the optimal and then sending data.
I see.
Because one of the things in like the topology of mesh networks is you can have multiple beacons connected to each other. So Batman tries to evaluate like if you go which direction through the hops is going to be most efficient.
I see. Yeah, that's really interesting. Huh.
Yeah. And then all our robots are also just basically another node on the mesh network. So they can just hop between beacons. It's actually really convenient because we can also just like move files between robots over this mesh network. And when we need to update the robots, we just have a node that's connected to the internet and passes internet to all the robots as well. But that's all obviously not at the actual event. Like the internet is not available to us inside these mines and nuclear power plants.
I feel like we've been on the slide for a bit, but I'm still interested in asking another question still.
Sure.
I'm curious if you can use, sorry.
I'm open to questions. Like I was just trying to see what you guys want to get like out of this presentation. So
yeah, that's good. Well, this is something I'm hoping to get out of. I'm wondering if you can use these kinds of networks to inform the localization process. Like, are the signal strengths deterministic with respect to length? Like, are these informative things, or is it typically more accurate and helpful to just entirely geometric map system, I guess?
So at least with like the dual antenna setups we have here, the signal strengths are not really reliable enough to get you any kind of, they're not like the Ouster, for example, does points in the order of like centimeters for accuracy. And this is probably on the order of like hundreds of centimeters at best, if not even like meter off. Now, there is, I'm not too familiar with it, but there are commercial products and research into, I think Cisco has a multi-array kind of Wi-Fi localizer that uses like 6 or 7 or maybe 8 antennas even. And those types of methods do tend to give you much higher accuracy because they can triangulate the signal from a lot more different points. I can't really speak too much to them. I haven't really worked with them, but I've just kind of seen that they're available at some point. So basically, to answer your question, not with the setup that's presented here, but I think there are setups that could do better. So as I was saying, this is everything gets sent back to kind of our base station. So this is an example of that interface. We kind of get the object detected back here. Our supervisor can see that object. And then over in this window, that's where it found the object. But sometimes if there's map drift that we can visibly see, or the object didn't get projected to the right spot for whatever reason, due to noise in the octomap or something like that, we project directly onto the octomap. So if there's noisy, it's conceivable you project to the wrong voxel or something like that. So he can drag that around to like wherever he wants to report it and send that coordinate back, which comes in very useful, especially with drift and things of that nature, which are really hard problems to solve. You can kind of see, especially when there's 2 robot maps, that one of them's drifted one way or the other. And so then you can, basically, a human can look at a map that has drift in it and kind of tell where it drifted. Especially when you have the second point of comparison. So that's really an easy problem for a human to go and like drag. But doing that autonomously is much harder to calculate like the drift between maps. We are using or developing like iterative point cloud based methods to align our maps better and things of that nature, but there's still limitations in those processes. This is that very much kind of a open area, is having reliably loop closed maps in kind of real time. Some of these ICP methods can take minutes to converge with a lot of points. So
But if you don't mind,
Sure.
what do you exactly mean by drift here? This might be a bit of a basic question, but I'm not familiar with the term.
Okay, so we'll try to figure to show this, but basically what kind of goes on is like if the robot's like, let's say my hand, can you guys see my video? Like if my hand's going straight and the robot is also going straight, but the state estimator, I think it's always going a little bit to the left. So then as you get farther and farther away, you're drifting from your real point. And a lot of that also, DARPA provides a reference frame in the form of a gate, and we localize that with a survey instrument and provide that transform to the robot. But that also has initial error. If you have rotation error, then it propagates the entire way through the run. If you have like a little bit of translation error at the beginning, it's not very relevant. Because if it's that's up to accurate to like millimeters and like 0.05 of a degree or something like that. But even 0.05 of a degree, if you like draw a triangle and go out along that ray for, you know, a kilometer, then suddenly 0.05 of a degree is quite a few meters of drift out at a kilometer. And then the state estimators are also inaccurate. So this is a combination of both initial position error and error as the run propagates through the state estimator.
I see. That makes sense to me. Yeah.
So then now we're really targeting this final event out in Louisville, Kentucky at this thing known as the Mega Cavern. And one thing to note about this image right here is this scale is about, each one of these is about a kilometer, each one of these like grid cells. So this is a huge, huge environment compared to anywhere we've been in before. Chances are DARPA's not going to send us through the entire environment, but even if they send us to like a quarter, it's still massively larger than anything we've explored before. For reference, in the mines, the hallways were probably maybe 8 meters across at most, probably less than that, like 5 meters. These are like 20 meter, each one of these caverns down here, like hallways, is 20 meters across. So it's a very wide open type of environment. So one of the things we I thought would be interesting to show is to get around the stair problem, a lot of this cave terrain problem and stuff, we have decided to go and buy Boston Dynamics Spot, which is the primary platform we're really trying to progress on right now, which can also explore these large environments much faster. It moves about double the speed the Husky can. And this is a pretty steep incline. It's kind of hard to tell from the video with like a railroad track and all this rubble, and the Spot just like walks up it like a champ, which is like really encouraging for us because for instance, at the tunnel event, like these legged robots are really, really hard challenge to solve. At the tunnel event, some teams were using legged robots and they fell like after 3 or 4 steps into the tunnel. It's just a really hard kind of problem that no one on our team has experience with. So being able to use Boston Dynamics Spot and just kind of build our autonomy stack around their controller and their platform that they've invested millions of dollars over the last however many years into developing is quite nice, actually. So I just thought that's like a really cool kind of robot to show off, and definitely one we're all very excited about to be using at the final event.
Hi. So I had a quick question. Are there any limitations on what platforms you guys can use just in general? Like, is there something like, could you go on, like, I guess the question is there any limitations on what you can pre-purchase, I guess?
I don't believe so. Everything has to have a e-stop safety inspection. So DARPA has a radio e-stop that they require the platform to stop all motion within like 5 seconds. That's primarily, that rule is there for UAVs and things of that nature so they can land safely. So apart from that, if it's a safety concern, DARPA would likely say something, but I don't think there's any explicit limitations anywhere in the rule about what you can and can't deploy.
Okay, interesting. Thank you.
They might not allow like gas motors and things of that nature because it's underground, but I have to double check that. I think everyone's using batteries for this.
This might be a pretty specific question, but like, what is the control interface with Spot? Is it X and Y translation or velocity based?
So basically it's velocity based, and then you can send basically poses for the body to like orient itself into. You can't really control individual joints or anything like that. You can really just command like overall positions of the body and give it like command velocities in different directions to go in. That aspect's a little disappointing. It's kind of locked down the API from Boston Dynamics to that. And the other kind of, it has RGBD cameras, which we assume are a variation of the RealSense, likely put with their own FPGA or something like that, but they also limit it to black and white for when you get the images back, which is, we're like, why would you do that in this day and age? But apart from that, it's been a pretty easy platform to work with because they've done a lot of the work for you, but integrating onto it is a little more challenging in the sense of it's smaller, so you need smaller form factor computers, fitting all the sensors on there, carrying more batteries, and it's only a 14 kilogram payload. So the built-in battery, if I remember correctly, runs for about an hour and a half under no load. But obviously, if you want to draw your computer power off of that and everything like that, then that battery is going to decrease more. So what we're doing is we're putting 2 batteries on there and letting the internal battery just kind of handle what Spot does. And we're building our own kind of module on top of it to do our autonomy stack.
Quick question with kind of adding stuff. I know, I mean, at least from my memory, this might not be exactly relevant, but that don't they like sell like modules for Spot? Like you can like go and buy like a LiDAR module or something?
They do.
Oh, they do? Okay.
One of the things with those modules, if you ever get a price quote on them, they're very expensive for what they are. Like they're selling an i5 computer that interfaces with the Spot for about $4,000, I believe.
Oh wow, that's crazy. Yeah.
So having our team has done like a lot of integration on the Huskies already, so we decided that we would rather invest in our own hardware and develop our own kind of solution. Because we also need specific sensors. Like the rest of our planning and mapping works with the 64 beam Ouster. I believe that they sell Velodyne lidars. So like the last thing we really wanted to do is have different sensors on different robots and have to deal with the mess of like homogeneous kind of fleets like that. Like at least now we know that our sensor driver is going to work reliably on all the robots, or it's going to work the same way on all the robots. And things of that nature.
Okay, yeah, that makes a lot of sense. Thank you.
And one of the things I guess I'll throw in there is like field robotics is, there's a lot of small stuff that goes into it that if you're doing just kind of like research in robotics and you need to just kind of write one paper with the robot, you don't necessarily have to think about, like for these kind of long scale deployments, things like time synchronization become a huge problem. Like synchronizing time between the robots. So like when maps come in there on time, that is not as big of a challenge as synchronizing like sensor to sensor time, like cameras lining up with the LiDAR. And just like various small issues, like I've learned a lot more about like Linux in general and like UDEV rules, how to like debug problems. Like we got like sometimes things would crash and you have to look at all the different logs for like PTP, which is the timing based kind of protocol, USB kind of logs, and just so much, there's like so many small things that they're like hard to like name off that you learn from field robotics and trying to implement all this kind of stuff. So then I kind of just wanted to give like my high level perspective of like the difference between industry and graduate school, at least if you're going into like a PhD track. And I kind of mentioned this earlier, but in industry, I really found that you're really solving problems that have already been explored and almost solved by someone else. So you're like resolving them. And typically once you get good at something, you're going to be the one who's responsible for that. And anything similar to that, you're going to just modify what you already did to like match that. For instance, I got good at figuring out how their databases at my previous company worked. So then I modified like databases in one place and was told to go make those same modifications to other ones. And that was kind of my role, and I didn't particularly want to stay in that role. So then, but in graduate school, what I found is for research specifically, you're really looking at problems that haven't been solved. Like one of the areas I'm actively trying to research in DARPA, like once the platforms are done and we can get to this point, is the difference between what is an explored area and what is an area where the cameras have seen, and how do you like deconflict between those in planning, and how to even tell where you want to go look for artifacts in the environment. Because, for instance, if it's a wide open room, DARPA does not tend to hide an artifact in a wide open room. They will definitely put it behind a doorway or like in some corner or on top of something. So like reasoning over the environment to kind of predict where DARPA might put things is another kind of unsolved problem that there's not really, you can't really just go like, Google the answer and see someone's developed a package that does this. It's something that you really have to think about on your own to solve, which is one of the reasons I like grad school. So that's kind of what I've done through robotics, and that's kind of the slides that I had prepared, but I'm happy to answer more questions or anything of that nature.
So we're a bit past 5 p.m., so we can definitely leave it open for some questions, but when you have to go, by all means, feel free.
Yeah, I can probably stay for another like 10 minutes or so.
Yeah, I think we can open it for questions. I definitely have some, but I think Ryan had something also.
Oh, I mean, well, I don't have, I guess, a lot in terms of questions. I would say that maybe one of my questions beyond this would just be, especially since you're bringing up industry versus graduate school at the end, like what your general experience, I guess, just being in grad school has been like. Maybe like what are your post-graduation plans? Do you plan on continuing to try and be in a role in a company that allows you to still focus on, as you described, like more unsolved problems?
So I definitely want to be in a role that does that. Whether it's in academia or industry is still kind of yet to be determined for me. At the current moment, I'd say I'm leaning more towards industry, but I still have probably at least 2 to 3 more years on my PhD, so a lot can change in that time. And kind of my general experience. So grad school is stressful, kind of in like different ways, I'd say, from undergrad. Undergrad, I was definitely personally more stressed about like coursework and making sure I was doing really well in courses. And what I found, at least in grad school, is the courses are there's less actual like homework and problem sets, but the ones you do get are much more challenging. But there's also, most of the professors do know that you're in there like for research and do a PhD. So the classes are, I don't want to say that necessarily scale, but they don't necessarily, the homeworks they give out, they don't necessarily expect you to get like really high marks on like they do in undergrad. They're much more like they want to challenge and see where you can go, but you don't necessarily need to have at least at CU Boulder. Like the expectation is not that everyone solves like 100% of everything. Because some of them are pretty open-ended, like problem sets that aren't just like there's a known solution to it. There's like multiple approaches to solve the problem and things of that nature. So I'd say classes are still somewhat stressful, but the chances are in grad school, if you do the work and if you're struggling, because I know people have come from different backgrounds and you've like met with the professor in office hours, they'll help you and you'll generally are going to pass no matter what in grad school, unless you're not doing the work. And if you're falling behind, not seeking out help from the professor. And I think partially that is, like I was saying, different backgrounds. Like some people in the program are from Mechie, some are from like even, I think there's like a geology major that moved into the computer science program. So like a lot of the faculty, at least here at Boulder, I don't know if at other schools, understand that not everyone has like the undergrad comp sci background or something like that.
I see, that makes sense to me. And I guess just for reference, I'm also currently doing my undergrad in ECE here.
Okay.
So that was really interesting to see, especially now that you're moving more into this, I guess, robotics type work.
Yeah. From that perspective, I would say like, I think electrical engineering was a good choice for me undergrad. I will say though, that if you want to go into robotics, the number one skill to have is like software development skills and really understanding what good quality software is, because you can really shoot yourself in the foot if you don't understand like things like memory management and how problems scale and different kind of algorithms and data structures. You really do need to know those things to write efficient code that's going to run for like long-term deployments and stuff like that. And primarily most of the like interesting problems, they're not like designing the circuit that controls the robot or anything like that. It's all in the algorithm that's going to run on the processor nowadays. Not to say that there aren't interesting like mechanical problems, like if you work on a robot like Spot or something like that, there's going to be interesting problems mechanically and things of that nature, but there's also equally, if not more, interesting software problems, which is why, in my opinion, knowing software is like a crucial skill.
I see, that makes sense to me. Yeah.
I think there are a bunch of ways, like a bunch of topics I could ask about, but one that comes to mind in terms of just like, this is directly relevant for the club. We're currently trying to join Robotics, which is a NASA-funded, like build a lunar rover and various levels of autonomy. Definitely less intensive than this. But I'm wondering how much of the software you used was like open source. You mentioned that, but like, what parts of the stack do you end up writing, and what are the most important components to have manual control over from the software side?
The primary stuff that the primary areas we've written, like almost all of it ourselves, has been in the path planning and controller aspect for the individual robots. There's a lot of, we've modified state estimators, but writing your own state estimator that performs reliably for long deployments is like, for instance, Google Cartographer, which is what we used originally until we moved to a more to a package known as LAOSAM and then modify that for our needs. If you look at some of the like author counts on those papers, there's like 10, 15 authors even. Google has like tons of their engineers that develop stuff into Cartographer. So it's just like a lot that goes into testing that. So I'd honestly recommend an off-the-shelf kind of state estimator if you can run it. It'll probably suffice for most of your needs. But keeping like your control and path planning algorithms closer to you is definitely important, because those really vary depending on the kind of solution you develop. Don't write any kind of like camera drivers and stuff like that. Definitely buy cameras that have a good driver support off the shelf. Same with kind of if you're doing like object detection, unless you have someone that really wants to research like state-of-the-art object detectors, you probably want to take an existing one and train new weights for it.
Okay, that's actually really informative for kind of what we're going through this semester.
Yeah, there's just like a lot of things that like, sure, everyone would love to dive in and really understand them, which would be great, but there's just a limited amount of time. So
I had a question about that was something like kind of far back. I forgot to ask.
sure.
For the urban challenge, like you were using like the Huskies, but you were also using the like more tank
Mhm.
robot for like stairs and stuff. Was there a reason why you like kept using the Huskies despite it not being able to go upstairs?
The tanks had really low ground clearance, which made them get stuck on obstacles really easily, which is one of the reasons we're not going to use them when we replace them with Spot in the final event.
Yeah, I was
So like
curious.
if there was like rocks and stuff on the ground, and that's really, those were harder to reason over. Our terrain planner wasn't acting like running on a dense enough kind of mesh net to determine where the small stones were. It was primarily running on the Octomap, which was like a 15 centimeter resolution, which for the most part, the Husky will go over obstacles that are like 15 centimeters or less, but the tank would not.
So do you think like using Spot has kind of like covered some of the disadvantages of both of those?
Absolutely. I'd say the Spot, our strategy is definitely shifting more to the Spot. It's going to be primarily ground exploration type robot. So it's going to go explore as many places as it can. And the Husky carries the communication beacons on the UAV now. So it's going to be much more of a support vehicle. It will still be looking for artifacts as it goes along, but it's going to be much more targeted at getting the UAV where it needs to go and building out this kind of comms network to send back to the base station. Because the Spot can't, obviously with 14 kilograms of payload, can't really carry many communication beacons or a UAV. It's kind of its own thing.
Yeah, that's interesting.
Yeah. There's a lot of strategy that goes into it as well, of like what you want each robot to do.
Is there a limit on how many like vehicles you're allowed, or
No, there's a cost kind of limit and a practical limit
Yeah.
of runs are 30 minutes at the final event instead of an hour. So there's only a certain number of robots you can like launch in 30 minutes. So there's like there's no like rule limit, but there's definitely practical limits.
Yeah, that makes sense.
And each robot also supporting each robot and configuring everything and getting it set up takes a non-zero amount of time.
So I think we could probably ask many more questions. This is definitely really interesting stuff. If no one has anything really pressing, I think we probably should wrap it up just to keep the recording down and let everyone move on. But this has been by far, I think, the coolest thing the club's done this semester. Thank you so much for taking the time to do this.
No
This is
problem.
fantastic.
Hope
Yeah.
you guys learned something.